Hello, my name is Tom Irvine, and I'm the instructor for this unit. And I thank the NASA Engineering and Safety Center, NESC, and Dr. Kurs Larson for making this webinar series possible. The unit for today, we will be synthesizing a time history to satisfy a power spectral density specification using random vibration. And this will be broadband random vibration with a normal distribution. Now, a PSD does not have a unique time history because the PSD discards the phase angle. And that actually allows us some flexibility for a shaker table test of a component, for example, because that allows the control computer to come up with any time history it can in terms of its own phase variation. And as long as that time history has a g² per hertz magnitude that satisfies the specification within some reasonable tolerance bands, then that time history can be used as a base input to the component or test unit, whatever it might be. Now, another reason we might want to synthesize a time history to satisfy PSD is we might have a finite element model and we may want to do a modal transient analysis. And that can be useful for stress and fatigue calculations, for example. So sometimes when we do vibration analysis, we like to do it in the frequency domain. Other times we like to do it in the time domain. And the results should come out the same regardless, but it's good to have that flexibility so that we can choose either or both. This slide here, it's actually a review slide. So imagine going to the control computer and typing in a power spectral density specification in terms of coordinate points. Well, that control computer has no way whatsoever to directly send a PSD via the power amp into the shaker table. But what it can do instead is come up with a acceleration g versus time in seconds time history. And actually it has to do another step yet, because what the control computer does at the onset is send a very low-level signal through the power amplifier into the shaker, and that gets picked up by the feedback accelerometer. So there's a control loop calibration process that goes on. So what the control computer will do then is take the g² per hertz versus frequency in hertz power spectral density, synthesize a corresponding time history in terms of g versus second, and then it will determine how to come up with the proper voltage versus time in seconds signal to output to the system. So here's how we're going to go about doing our synthesis with these 7 steps. And of course there's a lot. This is just an overall outline. There's some in-between steps and some additional steps as well, but this gives the general idea. So first of all, we're going to generate a white noise time history with a normal distribution, and this can be easily done using a function in MATLAB. Then we're going to take the fast Fourier transform of that time history. We will then scale the fast Fourier transform amplitude, or perhaps I should say magnitude, per the PSD g² per hertz levels for each frequency. Then the resulting intermediate synthesized time history will be the inverse fast Fourier transform, which has been, again, the FFT has been scaled in step 3. Now, when we do this, our acceleration versus time signal will have a mean value of 0. But typically what happens if we integrate it to velocity, a baseline shift occurs. And then if we integrate one more time to displacement, we get a ski slope effect that occurs. And neither of those are desirable for either the shaker table test or for just doing finite element analysis. So in step 5, we're going to use a series of integration steps and various polynomial trend removals and differentiation so that we can come up with a set of 3 signals, the 3 being acceleration, velocity, and displacement, so that for each of the signals in this set, the mean value will be 0. Then in step 6, we scale the time history, our synthesized acceleration time history, so its GRMS value matches the specification's overall GRMS value. And then there's a corresponding scaling for velocity and displacement as well. And the mean value of our time history is going to be 0, so we can use the terms GRMS and standard deviation interchangeably. And then the final step is 7 is just a verification step. We're going to take a power spectral density of our synthesized time history to verify that it matches our specification within some reasonable tolerance bands. So here's a power spectral density. It's called NavMat P9492. It's a Navy specification. We've talked about this one before. The overall level is 6.06 GRMS, and that's the square root of the area under this curve. The y-axis dimension is acceleration with unit g squared per hertz. Our x-axis is frequency in hertz, and this is defined in log-log format, so straight line segments in log-log format. Then the 4 coordinate points or breakpoints are shown in this table here. So let's go ahead and synthesize a 60-second long time history to satisfy this PSD. So we're going to go over to our MATLAB GUI package, and our GUI package is up to version 4.9. We go to power spectral density, time history synthesis, starting from white noise. Okay, so this particular function is up to version 1.2, and this script synthesizes an acceleration time history to satisfy a PSD beginning with white noise. Now, we're going to begin with white noise, but our resulting acceleration time history will typically not be a white noise time history. It'll still be broadband random, but if our PSD specification has various ramps and slopes and peaks and valleys, then the resulting time history, which is a synthesized time history, will not be white noise. It'll still be broadband random, and it still will have a normal distribution. So what we're going to do is I have the navmat points in an external ASCII file. So it's navmat_spec.psd. And we're going to do a 60-second time history synthesis. View the options. Now this is where we apply our critical thinking skills. And we're going to choose row 8. That'll give us 128 segments. Our time per segment, almost half a second. Our delta F is about 2 hertz. That's our frequency step in our PSD, with 256 resulting statistical degrees of freedom. So next we do our calculation, and take a few seconds, but not too bad. So maybe I should go through these one at a time, starting with figure 1. Well, actually, let's start with figure 2 here. So this is our resulting acceleration time history. It's been synthesized. It has an overall level of 6.06 GRMS. So we have acceleration versus time. And this signal, it's not white noise, but it is broadband random vibration. So if we zoom in, you can see, yes, in fact, it is a random vibration signal. Now, step 3 here is figure 3 is our corresponding velocity time history with a mean value of 0. And then we have the corresponding displacement time history, also with a mean value of 0. Now this is the acceleration histogram, and it has a nice bell-shaped curve, or you might say Gaussian distribution or normal distribution. So that's all very well and good. And then here's our verification step. So what I've done is taken our navmat PSD, and that's the red line here. That's what the software program plots for us, I should say. Then these tolerance bands are plus and minus 1.5 dB, so fairly narrow tolerance bands. And you can see that the resulting synthesized signal, the blue curve, is well within the tolerance bands. So it looks like we have a good synthesis here. And of course I should mention this is a power spectral density plot, acceleration g squared per hertz, which is really grms squared per hertz, and then frequency in hertz. So we would say now that acceleration time history is good to go. It could be used for a shaker table test, or it could be used for doing some kind of a modal transient in a finite element analysis. And actually what we're going to do is something quite simple, just a base input to spring mass single degree of freedom system. Now later on in future webinars we'll look at multi-degree of freedom response, and we'll look at responsive continuous systems like beams and plates and shells. So what we're going to do next is we're going to save this time history, and I'm going to call it the input underscore th for time history, because we're going to use this as an input for a single degree of freedom system. So I'm going to save that. It's going to go into the MATLAB workspace. And I'm also going to save the PSD. So this is the PSD of our synthesized time history. Input underscore PSD save. And we'll be using those files for some other purposes here shortly. Another thing I suppose we could do, just somewhat of a review exercise, if we go to time history and go to our statistics function, we can input our input time history, which is input underscore th, acceleration in g's along the y-axis. And we can get some more descriptive statistics for our signal. So, okay, this is the absolute peak value distribution. We're more concerned about doing this one for responses than for inputs. Cumulative histogram. Then here's just the bell curve histogram again. One of the neat things about going to the statistical module is we can change the numbers of histogram bars. We can play around with that, for example. So I'm going to change that from 31 to 41. So you can play around with that at your leisure. And then we get a few other parameters. We see the mean value is essentially 0. So standard deviation, RMS, come out the same. Skewness is close to 0. Now kurtosis, so for broadband random vibration with a normal distribution, we expect a kurtosis value of 3, and that's what we get if we round off. Then we see our maximum and minimum there. The crest factor, which is the maximum absolute peak divided by the standard deviation, is for our input 4.7 if I round that off to the first decimal place. So all the people that say 3 sigma is the worst case may be underestimating. But really, again, we're going to be more interested with crest factor in terms of the response of the single degree of freedom system rather than for the input. For broadband random vibration, the rise characteristic frequency, I'm not sure it means very much at all. This parameter is more of interest if we have something that's fairly sinusoidal. Okay, so what are we going to do next? Well, actually, we're going to go back to the slides briefly. And what I've done, I'm doing a live well, not exactly a live presentation, but I'm demonstrating the MATLAB scripts as an aside from the slides. But I also have an example in the slides, and the example in the slides will give a similar time history to the one I just demonstrated, but due to random number seed generation, that sort of thing, it won't be exactly the same, but its important statistical parameters are the same. So we went through and we did a time history synthesis, and again I'd like you to do this for your homework exercise. So I went through those steps there. And in the slides, here's what we got for the time history, which is now going to be a base input time history to spring mass system. So broadband random signal, it's not white noise, but it is broadband random with a normal distribution. And its histogram for the one in the slides, again a bell curve. And its corresponding PSD falls within the plus or minus 1.5 dB tolerance bands. Okay, so here's our next important step here. So our spring mass system, this is what we continually use over and over again in this course units. So we're going to take our synthesized time history and apply it as a y double dot base acceleration. So we're going to base drive this single degree of freedom system. You'll have mass m, and Hooke's law gives us the stiffness k. Then there's a viscous damping coefficient c, and x double dot is the acceleration response. Now in previous units we've gone through the process of taking the system, drawing a free body diagram, using Newton's laws to sum the forces and set that equal to mass times acceleration. And then we also found out that in terms of applying the base input in the time domain, after a number of steps we could derive what we call the Smallwood ramp invariant digital recursive filtering relationship. And that's the numerical engine we're going to use for our modal transient analysis. And for those of you that have previously done shock response spectrum analysis, you most likely have used the Smallwood algorithm, whether you realized it or not. And it was originally derived for that purpose, for short transient signals, but it works just as well for longer duration stationary signals or steady state inputs as well. So our natural frequency is 1 over 2 pi times the square root of stiffness over mass. You've seen this equation before. For our example, we're going to set the natural frequency equal to 200 hertz and our Q value, our amplification factor, equal to 10. So let's go back to our GUI package here. So let me type in vibration data. And we're going to do a time history, single degree of freedom response to base input. This is where we implement our Smallwood algorithm. This is up to version 1.2. This script calculates the response of a single degree of freedom system to a base excitation. The input data must have 2 columns, time in seconds, and base acceleration. So in this case, we have preloaded into MATLAB our synthesized time history, which is input underscore th. And we have our English units, 200 hertz natural frequency. And it's so common that we use Q is equal to 10. I actually have this as an initial value in this edit box, but you can change that if you have a different Q. So we're going to calculate, and calculation goes very quickly. We've got a relative displacement response time history, and eventually we're going to be looking at these, especially when we get to circuit board analysis, dynamic analysis of circuit boards per Steinberg criteria. And we'll also, when we do isolation, isolated systems, we have to look at sway space, and relative displacement will be of interest. But we're not going to consider it any further today. Here's the acceleration response time history. And then we have the base input time history, which we've seen before. We've seen base input before. That's what we synthesized. Now this acceleration time history, let's before we forget, let's go ahead and save this. I'm going to call it RESP underscore TH for response time history, because we're going to use this for some other post-processing steps. So I'm going to save that. Let's see what we get. Our RMS response is 11.4 GRMS. Then the maximum and min values are shown there. So our crest factor is 4.3. And there is a theoretical crest factor from the Rayleigh distribution. In fact, we can go to, let's see, if we go to miscellaneous, single degree of freedom response, peak sigma for random base input. Let's begin that analysis. So we've run this from before. Consider a single degree of freedom system subjected to a stationary random vibration base input. This script calculates the maximum expected peak response in terms of the sigma value via the Rayleigh distribution. So we have a single degree of freedom system, 200 hertz, and our duration was 60 seconds. So we expect our maximum peak. This is really the expected crest factor, 4.47 sigma. Well, for our case, we came out a little bit low. We came out 4.3, so maybe about 5% error, but You have to remember, when we're dealing with random vibration, we're in the realm of probability and statistics, so we're not going to be too concerned about being 5% too low. If we'd have taken a longer duration base input, then most likely our numerical experiment crest factor would converge to the corresponding crest factor from our Rayleigh theory. But that's all okay for right now. We might also want to stop and consider, what's going on with this response time history? Is it a broadband random signal? Is it beat frequency? Is it a damp sine? Is it half sine pulse? What do we get for our response acceleration time history? This is the absolute response. So if we zoom in a couple times so we can sort of qualitatively judge its character there. So again, we're applying some critical thinking skills. And we see that, well, it looks like the frequency is fairly sinusoidal. So if we disregard amplitude and only focus on frequency, it looks like a fairly sinusoidal signal. But the amplitude envelope kind of varies randomly with time. So we need a new way to describe this signal. And the new way we're going to describe this signal, this response, we're going to call it a narrowband random response. So we have a narrowband random response, and that's the response of the single degree of freedom system to the base input, the random base input. So what's the histogram going to be for our narrowband response? So the next thing we're going to do is, I think we're done here. Let's hit return. Let's go back to our statistics function here. And our input array is going to be RESP_TH. That's our response time history. Acceleration in G's. Calculate. Okay, let's go through these statistics. Well, the kurtosis value there is still about 3. That's interesting, isn't it? Figure 2. So here's the histogram of our acceleration response, and guess what? It's a bell curve. So for this narrowband random response, we still get a bell curve histogram. And this is a histogram of the instantaneous values. And here's the response acceleration time history itself, which we've seen before. What other plots do we have here? Cumulative histogram. Someday we're going to be interested in that, but I guess not today. Now here's an interesting one. It's called the absolute peak value distribution. And this is a histogram where we have counts versus the acceleration G level, but it's a histogram only of the positive and negative peaks. So imagine taking this whole time history, and we're going to do a data reduction. We're going to reduce this time history so we're only retaining the local peaks, whether they be positive or negative. So we're going to take all our localized peaks and in a sort of a subset time history, and we're going to take a distribution, a histogram of that subset, and it's going to be what we call a Rayleigh distribution. And if we want, we can play around. We can maybe have a finer number of bars. So I'm going to change from 31 to 41. Get a better idea what it looks like. Smooth it out a little bit. So this is the Rayleigh distribution of the local peaks. And this sort of distribution could be important, for example, if we were doing a fatigue analysis. Let's see what else we have here. The statistics also gives us the crest factor. Again, we came out about 5% low, but we're not going to worry too much about that. Now, here's something interesting. Our Rice characteristic frequency is almost 200 hertz. Well, 200 hertz is the natural frequency of our spring mass system. And what this is telling us, if we were to go and take some small time interval where we could reasonably count the peaks. So let's see, if I go from 23.6 to 23.7, that's a tenth of a second interval. How many positive peaks do I have? Well, I'm going to roughly count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So over a tenth of a second, there are 20 positive peaks. So if we extrapolate that up to a full second, we would have 200 positive peaks, and that's equal to the natural frequency of the system, also confirmed by the Rice frequency. And if you're wondering what the Rice frequency is, we've actually covered it before, but let me show you. If we go to our vibration data blog, we can click on Rice characteristic frequency. So what we do is if we have our response amplitude y, and we take its standard deviation, well, it could be an input, it could be a response, it could be any signal whatsoever, but it's just the amplitude of the time signal, of the time history. So in the denominator, we have the standard deviation of the signal. In the numerator, we have the standard deviation of the first derivative with respect to time of that same signal. Take that ratio, divide by 2 pi, and that's our Rice characteristic frequency. Okay, so the next thing we're going to do is we're going to calculate a power spectral density of our response time history. So let's go to power spectral density, and we're going to go to our input domain is going to be time history. So we click on power spectral density, and spectral density is various. And there's 3 different types of PSD related functions there, and we're going to use the top one, which is PSD. And this should all seem familiar to you because we did a similar thing in our last webinar for the case of white noise. The difference this time is we have a time history that satisfies a shaped power spectral density specification. So it's going to be preloaded into MATLAB, acceleration G. It's going to be, no, it's not going to be the input, it's going to be the response time history. RASP underscore TH, lowercase. Mean removal, yes. Handing window, yes. We're going to plot from 20 to 2000 hertz. That's the frequency domain for the original NavMat spec. So again, this is a review, but this script calculates the power spectral density of a time history. The input array must have 2 columns, time in seconds and amplitude. For the processing options, we're again going to do the case where we have a delta F of about 2 hertz, which is row 8. Okay. Calculate the PSD. And before I forget, we're going to save this. So we're going to save this as response, RASP for response underscore PSD. Let's save that. That's now completed the save. Cumulative RMS function. Not particularly that interested in this today, but it does go up to 11.4 GRMS, which is our response overall level. And you can see what a rapid transition it makes at 200 hertz, which is the natural frequency of our spring mass system. So cumulative RMS is GRMS versus frequency in hertz. I should have said that at the onset. Now, here is our response power spectral density. And we already knew from the time history that it was 11.4 GRMS response, and that's confirmed in the frequency domain. So we have acceleration, g squared per hertz, which is really GRMS squared per hertz, log-log format, and versus frequency in hertz. Now down at the lower frequencies, we have a situation of unity gain. That'll become more clear in some of the next steps we're going to do. Then around 200 hertz, we're getting our resonant amplification effect. And then the system filters out the high frequency energy. And there's actually a couple better ways to look at that. So we're going to do that here momentarily. Here's now this input time history is the input time history for our PSD calculation, but it's really the response time history from our spring mass system as subjected to the NavMat base input. So what we can do is we can go to return, and under miscellaneous we have a plot utilities which will allow us to plot 2 PSD functions. So we're going to begin the miscellaneous analysis, PSD, plot. excuse me. We're going to do two curves of miscellaneous. Okay. Our first curve here will be a response PSD. So I'm going to say response for the title. I guess we could also put in its overall RMS level, 11.4 GRMS. Color it blue. The second curve is going to be our input PSD. That's the NavMat PSD. It's going to be our base input. It's going to be, I'm just going to say 6.1 GRMS. Let's make that a red curve. Our x-axis is going to be frequency in hertz. Log. We're going to do manual domain limits, 20 to 2000 hertz. The y-axis is now going to be acceleration in g² per hertz. Make that a log plot. We're going to use automatic limits. Figures, sometimes we might already have an existing figure 1, so that could be a potential conflict. I'm just going to say figure 10, legend on, grid on, and I'm just going to say power spectral densities. And we can have a couple choices. We can plot one curve. Okay, we've seen this before. That's our response PSD. Looks like we've got a couple extra decades represented there. And we can plot curve 2. That's our base input PSD. When I say base input PSD, it is the power spectral density of our synthesized time history, which was generated to satisfy the NavMat PSD. And then we can plot both curves. So here's a plot with both curve, and if we decide we have too many decades, we can make manual changes here for our y-axis limits. It's pretty easy to do. Okay, so what's going on here is now it becomes more clear. So we've got power spectral densities, g² per hertz versus frequency in hertz. Here at the lower frequency we have very nearly unity gain. So response approximately equals base input at the lower frequencies. Then as we progress towards higher frequencies and we approach our resonant frequency at 200 hertz, we get the dynamic amplification effects occurring. And then as we go to higher frequencies yet above the natural frequency, then we get this mechanical filtering effect going on here. And this crossover frequency should be approximately equal to the natural frequency times the square root of 2. Approximately. So I think that works out to be about 280 hertz or thereabouts. Okay, so this is just another way to look at our data. This gives us a better idea of how our base input is resulting in the response there. Now, for the spring mass system, sometimes we refer to that as a mechanical filter. And as you recall, we use the Smallwood algorithm, which is a ramp invariant digital recursive filtering relationship. So the filtering is it kind of refers to two things. It refers to the fact we're filtering out this high frequency energy. And in some sense, our spring mass system is acting like a bandpass filter, and that it amplifies energy about its natural frequency. But then keep in mind it has unity gain at lower frequencies. So in some sense, it's behaving like a bandpass filter, or in other senses, it might be more proper to say it's acting like a low-pass filter. But you get the idea of what's going on there. A couple other things we want to do is we'll just exit out of the plotting utility there. So for power spectral densities, if we have a pair where we have an input and response, we can do a power transmissibility function. So let's go to the power transmissibility function. So each array must have two columns, frequency in hertz and PSD in unit square per hertz, which is typically going to be g² per hertz. So for our response PSD, this is what we have already in MATLAB, RASP underscore PSD. Our input PSD is going to be input underscore PSD. This will be a power transmissibility function, and it's going to be called trans. It's going to be g squared out over g squared n. So anytime you have a transmissibility function or transfer function or anything of that ilk, please make sure you understand whether it's g squared out over g squared n or g out over gn. And likewise, if you're generating a plot, please duly note what it is. 20 to 2000 hertz. Calculate. So we're going to calculate our power transmissibility function. And before I forget, I want to save this. I'm going to save it as trans for internal MATLAB workspace purposes. Okay, so let's go back to this plot here. So this is the response PSD divided by the input PSD. And we get a very nice clean curve there. Now 10 to the 0 power is equal to 1. So, well, let me back up. We have transmissibility g squared out over g squared n versus frequency in hertz. So this is a frequency domain function. 10 to the 0 is equal to 1. In our low frequency end, we have unity gain. Then as we approach our natural frequency, we get the resonant amplification effects, and this peaks out at about 100. Then at higher frequencies, we get attenuation. Now, there's something very interesting about the fact that at the natural frequency, this comes out to be 100. In fact, let's zoom in. It's not going to be exactly 100, but pretty close. And this is one of these times when we need to be careful. So it turns out for the special case, now again this is a special case, we have a single degree of freedom system, and it is driven at its natural frequency. So this is a resonance case. So we've got a single degree of freedom system, spring mass system, it's driven at its natural frequency, or you can say resonance. So the peak power transmissibility is equal to Q squared. So our Q value for this case was 100. Excuse me, our Q value is 10. Q squared is 100. That is also our peak power transmissibility at the natural frequency. So you might think at this point, all I need to do is, it doesn't matter whether I have a multi-degree of freedom system or a series of spring masses or beams or plates, whatever. All I need to do is go to the power transmissibility function and pick off what the Q values are by just looking at the peaks. Well, no. Please do not do that. This only works for very special cases like this one shown here. Imagine, for example, you have a cantilever beam, and you're doing a base excitation of that cantilever beam, so you're exciting its bending mode, so a transverse excitation of the beam. So in other words, the beam is projecting out perpendicular to the base excitation axis. So imagine you put one accelerometer at the free tip of that beam, and you put another one kind of closer to the fixed boundary. Well, it turns out wherever you put that accelerometer is going to determine the magnitudes of your power transmissibility function. So that's why we can't just simply pick off the peak values and call that the Q. What we need to do instead is use something like the half-power bandwidth method. And it turns out, regardless of where that accelerometer is mounted on this hypothetical cantilever beam, we can still use the half-power bandwidth method in order to determine what the Q value is. So we've done this before. Let's kind of a review exercise. So I'm going to go, I've got to get a data cursor up. So I'm going to click on the spectral peak here, and the y is about 100, which is Q squared. The fact that that's not exact, it doesn't really bother us. Then we're going to do a couple things here. We've got to go to selection style mouse, so that'll allow us to interpolate. Display style, don't worry about that. Create new data tip. Okay, the half power bandwidth points, or we also call this the -3 dB points. So the y is about 100. So let's find out, let's set y is equal to 50 roughly by moving this cursor around. And I guess 51 would be a little more better for experimental purposes. But we're not going to agonize too much over getting something very exact. Create new data tip. Okay. So what we have here are very approximately the two minus 3 dB points, the half power bandwidth points. And it looks like the difference between those 2 points in terms of frequency difference is about 20 hertz. Now I'm just, when I say it's about 20, well, let's go ahead and be a little more precise than that. If it was 20 hertz, we'd get the exact answer I'm looking for, but I guess we're going to be a little more precise. And let's see what that frequency difference is. 20.9 hertz. So that's our frequency difference, is 20.9 hertz. So if we take the 20.9 hertz frequency, which is our minus 3 dB bandwidth, and we divide it, we divide it into, so we're going to take our natural frequency, which is, I'm going to round it off to 200, even though our peak's at 199.1. If we just do this little division step, it comes out to 9.56. So our Q value experimentally is about 9.6. And if we want to just be a little lenient, we could round that up and say, oh, its Q is equal to 10. So that's how you do a simple 3 dB bandwidth method. And what you can actually do is go to vibration data GUI script here. And if we go to damping functions, and I still need to fix these names a little bit. We just did the half power bandwidth damping, but we actually want to go to damping value conversion. Now sometimes the conversions depend on natural frequency, other times they don't, but let's go ahead and be all circumspect here and put in the correct natural frequency, 200 hertz. So our 3 dB bandwidth delta F is going to be, let's see, this is our delta F hertz, which turned out to be 20.9, so I'm just copy and paste that. Okay, so we get 9.569 for our quality factor, also called amplification factor Q. And let's round off and just say its Q is equal to 10. Fraction of critical damping, also known as the viscous damping ratio, is about 5% if we multiply by 100. Loss factor is about 0.1. That's twice the fraction of critical damping. Then there's a few other damping metrics here. Of course, we already know that we have this particular 3 dB bandwidth, delta F. A couple other metrics that you may or may not come across, but they're available if you ever need those. This first set of 3 do not depend on what the natural frequency is. But when we go from 3 dB bandwidth to this first set of 3, yes, we need to have the correct natural frequency entered. Now there's another thing we can do. We can kind of do a curve fit thing. And again, I have a slight bit of misnaming here. We're going to do actually an extension of the half power bandwidth. We're going to do a curve fit to the theoretical power transmissibility function. And it's sort of an extension of the half power bandwidth method. So what we do is, well, let's read this. This method performs a curve fit. It's trial and error using random number generation with some built-in convergence to determine the damping ratio for a system excited by base excitation or an applied force. This method is equivalent to the half power bandwidth method. Well, actually, it's an extension of it, so I need to change that. The input data must be a frequency response function. And it's going to be fairly important that we get some of these things just correctly entered. So we've got preloaded into MATLAB our power transmissibility, simply known as trans. Got a base excitation function. It's going to be acceleration, and this is very critical we get this right. We have amplitude square. Since we're dealing with g squared out over g squared in, we need to select amplitude squared. And then we're just going to plot the transmissibility function. And really, our transmissibility function is only valid between 20 and 2,000 hertz because that was our specification. And beyond that, we kind of just have a very low-level noise at higher frequencies. So the power transmissibility doesn't really matter much when we're just down in the noise. So let's just do our manual limits for our x-axis plot. So 20 to 2,000 hertz. And we've actually seen this power transmissibility before, only now it's a linear. Okay, now we want to sort of zoom in on the spectral peak a bit. So what we're going to do for our curve fit over in this right lower corner here, we're going to start at 100 hertz and go to 300 hertz. And that'll be the frequency bounds for our curve fit. So you can see we've got a good curve fit going on here. And we can look at real time. Every time we get a new best case for our curve fit, we see the numbers change and the graph change. So 200 hertz system Q is equal to 10. So it turns out for this case, at least to the number of significant digits shown, our theoretical curve fit gave us exactly what we were expecting, both for the natural frequency and for the Q value. Now, if you repeat this exercise and you get 9.8 or 10.2 for your Q value, don't worry. Don't worry. We don't want to really agonize too much over this. But we did get a good curve fit here, so now we have even more confidence in our estimate of what the natural frequency and Q value are. Of course, we knew what they were for the onset, but now you can imagine, for example, if you had a shaker table test and you had a base input time history and you had a response time history, then you could go through this same process here, forming the transmissibility function and going through the 3 dB bandwidth method and or this curve fit method to identify natural frequency and the damping ratio. Okay. So we've had some fun doing that. Another thing that we can do is, do you remember Miles' equation? I think we covered that last time. If we begin miscellaneous analysis on Miles, and what was our natural frequency? It was 200 hertz for our spring mass system. Now again, the Miles equation calculates the response of a single degree of freedom system to base input PSD. But it assumes that the PSD is flat from 0 to infinity hertz. Now if you go back to our, let me go back clear to the spec here. 200 hertz natural frequency. Now that's in the flat portion of the PSD. And we had sort of a rule of thumb for Miles' equation that we could use it if the PSD was flat over at least one octave on either the lower frequency, the lower or higher frequency end of our natural frequency. So if we go to 200 hertz and subtract 1 octave, we're at 100 hertz. We're flat over that domain, and we even exceed our requirement, which in this case exceeding is a good thing. So on, below our natural frequency, we're doing even better than meeting our criteria. But above the frequency, we're going to fall short a bit, because if we add 1 octave to 200 hertz, that takes us up to 400 hertz, and this break point occurs at 350 hertz. So we come close to satisfying our rule of thumb, but we kind of fall short because we do have some energy loss there relative to the white noise assumption. But we can still kind of more or less wave our hand a little bit and use Miles' equation. So if we go to Miles' equation, oops, where were we now? Okay, let's call up our vibration data, Miles' equation. Okay, we already have our 200 hertz, Q is equal to 10. Now our G square per hertz level, and you can go back and verify this yourself, at 200 hertz, that plateau region was 0.04 G square per hertz. Calculate. So according to Miles' equation, our overall GRMS response should have been 11.2. And if you recall, for our little numerical experiment, we're 11.4 GRMS. That agrees fairly well. And then we get a couple other metrics here. We get the 3 sigma value, which is 3 times the GRMS, with the implied assumption of zero mean. And then there's some parameters here for the relative displacement overall levels, and we've got that both for English and metric units there. So that's Miles' equation. Now in our next webinar unit, we're going to be learning what I call the better than Miles equation method. I like to teach you Miles' equation since it's so widely used, but there is a better way, and I will teach you that in the next webinar. Now if you go back through the class slides here, I just do the same thing I demonstrated, where we synthesize a base input time history, verify it has a normal distribution for its instantaneous values of its, so this is the histogram in other words. Verify that its power spectral density satisfies the NavMat spec within plus and minus 1.5 dB tolerance bands. Then we applied the synthesized base input time history to a spring mass single degree of freedom system. Calculated the response in the time domain here. Now the crust factor came out a little bit higher here, 4.69, and I think the theoretical crust factor is actually supposed to be 4.47, so I think I need to go fix that slide. But nevertheless, in this case, the crust factor came out a little bit higher than we expected. Then if we zoom in on the response time history, we can see that the frequency content is fairly sinusoidal at 200 hertz, but the amplitude, the envelope of the amplitude is varying randomly with time. And here's our histogram. This is of the response acceleration. So our response acceleration for 200 hertz, Q is equal to 10, is a normal distribution. So it's a narrowband process with a normal distribution. Then we also looked at the, again, this is our response time history, but now we're looking at the histogram of the absolute peaks. So we take the local peaks, whether they be positive or negative. We save only those peaks and discard the rest of the signal, and then we take a histogram of those peaks, and it turns out to be a Rayleigh distribution curve. Then we have our response acceleration time history, which is now converted to a power spectral density. In this case, the overall level turned out to be 11.3 GRMS. And you can see the various information there, the natural frequency and Q I've restated. And the peak level, if we take the base input, which was 0.04 G square per hertz, let's see, it'd be about right here. Then we multiply by Q square, which is Q square is equal to 100, then that equals our response PSD level. But this is a special case. It's a spring mass system, single degree of freedom system. If we have a multi-degree of freedom system or a continuous structure like beams, plates, or shells, then we cannot simply pick off the Q values by taking the square root of the peak responses. Instead, we have to use the 3 dB bandwidth method or the curve fitting method. So in this case, I have the two curves lined up, both the response and base input PSDs. And then I have a power transmissibility function of those two curves, a ratio of the response PSD divided by the base input PSD. And then here we have the, just picking off the minus 3 dB points from the curve, so we can do our 3 dB bandwidth method. And then for our half power bandwidth or 3 dB bandwidth method, we simply take our natural frequency, divide by the delta F, where the delta F is the frequency bandwidth for the half power points or minus 3 dB points. And if we kind of simplify, round off and all that, we get to 200 hertz divided by 20 hertz is equal to 10. That's our Q value. Then if we want to be a little more sophisticated, we can do the half power bandwidth method extension, which is really the curve fit method. And I've shown you all the parameters here. Please use these, especially the one I sometimes make the mistake is I forget to indicate its amplitude squared. So you need to have amplitude squared to get the correct output parameters from this. And in this case, it didn't quite work out quite as well as the one I showed you, but close enough. 200.2 hertz, and Q is equal to 9.7. So that's the curve fitting method. Then we also, just as a review exercise, did the Miles equation. So I hope you enjoyed this webinar unit, and if you have any questions, you can contact me. I've got a couple of different email addresses, and this one is as good as any, tom@vibrationdata.com. So thank you for your participation today, and have a good day.